now. So welcome everyone to today's Astroparticle seminar. And I'm happy to introduce you to our speaker today is Marco Chianese from the University of Naples. Marco did his PhD at Naples. Then he was a postdoc at Southampton in England. Then he was a grappa in Amsterdam. And then he came back to Naples as a postdoc where he is currently. Marco has worked on a variety of topics in astrophysics, particle physics, and astroparticle physics. I'm going to name a few here. He's worked on SUSY grad unification theories at LHC, on neutrinoless double beta decay, and exotic matter connected to wormholes, leptogenesis, and early universe cosmology, decay of heavy neutrinos, axions, and even gravitational lensing. He has also worked on characterizing the flux of high-energy astrophysical neutrinos, including neutrinos from starburst galaxies most recently. And he has also, this is going to be the subject of today's talk, worked prolifically on the dark matter probes using high energy neutrinos, both in connection to IceCube from different angles, and in most recently in upcoming neutrino telescopes as well. So today we're happy to have him talk about probing heavy dark matter decay with neutrino telescopes. Marco, thank you very much.
Okay, Mauricio, thanks a lot for the introduction. And actually, to me, it's a really pleasure to give this talk today. Yes, so today I'm going to discuss about possible probes of heavy dark matter in present and future neutrino telescope, ranging from a few hundred GeV to very heavy dark matter. And this work, this talk has been related to these 4 works that have been done with my collaborators in Napoli, as well with my collaborators in Amsterdam. So, okay. So as you probably know, there exist several astrophysical and cosmological observations that strongly suggest the existence of a cold non-baryonic matter in the universe, known as dark matter. In particular, starting from the galactic scale at a distance of more or less 10 kiloparsecs, we have the measurement of the light curves, so the velocity of stars inside our galaxy and other galaxy, and this deviates from what is expected baryonic and visible matter. And so in this case, you need to introduce an additional component to baryonic matter in the galaxy, known as dark matter, to explain these rotation curves. Then going at a larger distance, for example, in galaxy cluster, we have the anomalies known as the mass to light ratio. Also going to larger distance, we have the incredible observation of the Ballet cluster that can be regarded and considered as a collision between 2 different galaxy clusters, where also here they're able to trace back the baryonic matter here in red, and the dark matter that is more or less collisionless, but also at different time in the universe, so in the early universe, like the measurement of the cosmic microwave background, in particular the anisotropy of the temperature of the CMB made by Planck experiment, also suggests that, requires the addition of dark matter, and also the n-body simulation that model how the structure formation, basically the galaxy in our universe form. So all these gravitational anomaly, I will say, at different distance and a different time in the universe all suggest the existence of dark matter, and can be also explained and accounted for by the dark matter paradigm. But what is the dark matter? So as you probably know, the most studied particle for dark matter is known as weakly interacting massive particle, WIMPs. So these particles are generally particles with a mass close or around the electroweak energy scale, so around the GeV up to 100 TeV in mass, and have an interaction similar to the electroweak interaction. So this particle, this WIMP has been a lot studied and searched for in experiments, because generally extension of the standard model typically predict particles at this scale. But unfortunately, no detection at Collider, like experiment or other facility, have not detected yet this kind of particle. And so year by year, in particular the cross-section of the WIMP particle with baryonic matter, with non-particle, is function of WIMP mass here between 1 GeV up to 1 TeV. So all this region here that can be explained, I mean, is related to the dark matter parallel space is already excluded by, for example, that experiment. So given the observation of WIMPs, all the community has been increasingly focusing on different well-motivated paradigm for the matter and particle for the matter. So going to like dark matter with a mass below the WIMP energy scale, we have well-motivated candidates, like, for example, Chianese neutrinos, or the axion, the custody axion at very light energy, so at micro electron volt, or in general axion line particle. But in principle, in all this vast dark matter landscape, we could also have a very heavy dark matter, and also in this range where the dark matter mass is larger than more or less 100 TeV, we have many well-motivated candidates, like just to mention some of them, WIMPzilla, FIMPzilla, or particles that are produced through gravitational wave, or even heavy stellar neutrinos. So in this talk, I'm going to generally focus in this energy range. So I will use neutrino data, current and future neutrino data to probe heavy dark matter with a mass between 100 GeV up to 10 to 15 GeV. So the question now is in turn, so how we can really probe and explore this parameter space, or in particular, we can explore heavy dark matter, knowing that I mean, these mass, in particular these energies, are well beyond the energies that can be currently be achieved in man-made accelerator and laboratories. For example, like see the central mass energy is more or less 10 TeV, so it's well below this very energetic part. So how can we probe for this heavy dark matter? So the answer is through multimessenger and direct searches. So the idea here is that we can use the most energetic particle I've observed, which are basically cosmic ray, electron and positron, gamma rays, and in particular neutrinos, to probe indirectly this dark matter particle. Indeed, also suggested by the rotation curves of our galaxy, we expect the dark matter to be present in the center, or in general our Milky Way or in the galaxy. And so these dark matter particles that are accumulated here in the galactic center, depending on the interaction with non-matter, decay or annihilate between themselves. And this interaction, they can produce proton, electron, and positrons, gamma rays, and neutrinos. And this particle basically propagates in our galaxy and interstellar intergalactic space, and then reach us. So clearly, the neutrinos are the most clean messenger to study the matter properties, because as we know, I mean, they are weakly interacting with the baryon matter. Also, they do not are not deflected by magnetic fields, so they are the most clean messenger in terms of energy and arrival direction, so they can trace back the source that have been produced. But most importantly, we need to really include all these messenger to study in a more robust way the properties of the matter, and hopefully to claim for its detection. So let's focus on neutrinos in this talk and have a look at the so-called granular neutrino spectrum. So here is the energy flux of neutrino as a function of energy neutrinos. And so in all these very wide energy range, we have a lot of neutrino flux from our universe. Most of them have been already detected, like the solar neutrinos, the atmospheric neutrinos. Others are just modeled by theory, like the cosmological neutrino background or cosmogenics. So in this talk, I'm going to focus to the very energy neutrinos, so basically atmospheric neutrinos, the high energetic neutrinos observed by IceCube, and the modeled cosmogenic neutrinos. And so as you can see in this plot, the energy flux of all these components, in particular the energy of 10 to 15 electron volts, is more or less at this order. So we expect the neutrinos flux to be at the order of 10 to minus 13 centimeters square over a second. So before going to detail our dark matter model and limits of dark matter, so just try to understand what is the mass and the parameter of the matter model that is able to explain these flux here. So again, just to give a estimate what is the expected flux for neutrinos. So here I'm just considering the dominant component for the neutrino flux produced by the matter. In particular, this is the galactic component. So the matter, again, that is inside and accumulating in our galaxy and then can annihilate or decay into neutrinos. So in the case of annihilation, as you can see, the flux is proportional to the square of the density of dark matter in our galaxy, because we need two dark matter particles to collide, and then it's proportional to the thermally average cross-section, which basically tells us what is the rate of interaction of dark matter particles with themselves. So just plug in the number. So for a dark matter mass of 10 PV, so 10 to 7 GeV, and considering the local density here, the dark matter local density, expect the mean velocity of the matter particle in our galaxy, we see that we expect that the neutrino flux from the annihilating dark matter particle, it has to be smaller than 10 to minus 19 centimeters square over centimeter square over second. And this is because the cross section, which is a parameter that is related to the particle properties of dark matter, is constrained by theory, in particular from the requiring that this cross section and the scattering process is unitary. So we have this theoretical constraint, the so-called unitary constraint, that constraint from above the cross section. So the cross section cannot be larger than this value, and so in corresponding, given this upper bound, the neutrino flux from annihilating dark matter cannot be as larger than this value. On the other hand, for decaying dark matter, we have a different dependence on the physical around the particle parameter of dark matter. In particular, in this case, the flux, the neutrino flux, is only proportional to is directly proportional to the density, because we just need the dark matter to decay. And now the rate is given by the 1 over the lifetime. So the smaller the lifetime, the larger is the decay rate, and so the larger is the neutrino flux. So if we plug this number, so for the same mass here, and for a lifetime of the order of 10 to 20 seconds, we see that we get the correct order of magnitude that we need to explain this neutrino flux observed by IceCube. So again, for annihilating dark matter, we only have an upper bound, so this typically is not able to explain the fluxes of high-energy neutrinos above 100 TeV. On the other hand, for decaying dark matter, plugging this number, we get the correct flux that we need to explain high-energy neutrinos. So to probe for annihilating dark matter, we can indirectly, we can use atmospheric neutrinos, so they have an energy below 10 to 5 GeV. On the other hand, IceCube data, so high-energy neutrinos observed by IceCube, and cosmogenic neutrinos with energy well above 10 to 5 GeV are suitable to probe decaying dark matter. The final ingredient, the additional ingredient that we need to model the neutrino flux and also the flux of the other cosmic messenger is the particle spectra. So depending on the interaction that the dark matter can have with known matter, visible matter, the dark matter can decay or annihilate in different finite states. So they can be the production of leptons and neutrinos directly, for example, here from the decay of the dark matter particle in the sky. We could also have quark-philic dark matter, so the dark matter mostly interacts with quark, so hadronic matter. Or we could also have electroweak boson finite states, where in this case the dark matter predominantly decay into W or Z boson or directly to the Higgs. So what we need to model is the spectrum, for example, of neutrinos that are produced for each decay or annihilation of the matter. The key message here is that at the high masses, so for dark matter mass above the 1 TeV energy, so above 10 to 3 GeV, electroweak correction are relevant. So electroweak correction means that in this process there can be the production non-perturbatively of electroweak bosons, and this could decay into other particles like neutrinos or gamma rays that in principle are not expected directly from the process. So there are different codes in the market that are able to compute this particle spectrum from heavy dark matter. In particular, there is the Monte Carlo simulation by PITIA, the famous particle physics cookbook by Cirelli, the PPC code, but recently has been released the new code named as HDM spectra. So in this plot, indeed, you see this energy spectrum of, in blue are, in yellow are for gamma ray for photons produced by dark matter decay into neutrinos, and in blue you see the case of neutrinos. So in this, without electroweak correction, we do not expect photons to be produced in this channel because there are only neutrinos, but including electroweak correction, and in particular the production of electroweak boson, we have the production also of photons directly from dark matter. So here you see that all these code actually have different prescription to compute this spectrum. In particular, only HDM spectra recently include all the correction to the particle spectrum. And so you see that in principle, there are variations to this spectrum. So this is the number of neutrinos or photons as a function of this adimensional quantity, which basically is the energy of particle. So in this talk, I basically use different neutrino data sample to constrain and probe and looking for signature, indirect signature of the matter. In particular, I will discuss about atmospheric neutrinos with the energy below 100 TeV. I will discuss about astrophysical neutrinos in this energy range, so between 100 TeV up to 10 PeV as observed by IceCube, for example. And then in the last part of the talk, I'm going to discuss about Cosmogenic, with the energy expected to be larger than 10 PeV. So before going to detail of this talk, I mean, are any question on the neutrino flux produced by the matter, on the the ingredient that we need to model them?
So maybe one thing I actually want to know, you might touch upon this later, and then it's okay if you leave it later, but are there any constraints from cosmology on super heavy or heavy dark matter?
I mean, of course, I mean, in general, depends on the model. Of course, I mean, you need to, so in this talk, I'm just going to tackle the dark matter paradigm from a phenomenological approach. So I'm not going to discuss actually any model. But cosmological constraint depends in particular on what are, I mean, how the dark matter is produced in the early universe in the first place. So it depends on the production mechanism, basically. Of course, the one constraint from decaying dark matter, one naive constraint is that the lifetime should be larger than the age of the universe, because we actually see and observe them now. But as you can see, I mean, this is already fulfilled because we need lifetime which are many order of magnitude larger than the lifetime.
Right.
That we need to account for IceCube neutrino, for example. Then there are also some constraints on the that can come from the reheating process or inflation, but normally depends on how the matter is produced. So typically, it's constraint effect for dark matter that are produced through gravitational interaction, for example.
Okay, thank you.
Okay.
I think we can move on. Yeah.
Okay, so if there are no other questions, so I'm going to focus on the first topic, which are neutrinos. So these neutrinos are produced by cosmic rays that interact in our atmosphere. And so in this interaction, that are produced, for example, pions and kaons, and these can decay into charged leptons and neutrinos, and this is known as conventional neutrinos. But they can be also, that is still under study, the production of charmed meson, and these also can directly decay into neutrinos, and this component is known as atmospheric prompt neutrinos. So in this plot, you see a collection of measurements of the atmospheric neutrino flux as function of the energy, given by different neutrino telescope like Super Kamiokande, IceCube, and the recent Antares release here in black data. And the point here is that this observation is an irreducible background for the matter searches. So any possible signature from the matter will be seen as a bump or a deviation from or an increased flux from these flux. This is observed, and it's also well studied and modeled from simulation and theoretical calculation. So for this case, I'm going to discuss a forecast analysis of a potential probe of heavy dark matter in this energy range with the future KMT-net ARCA telescope. This telescope, is under construction and will be is built in the Mediterranean Sea. So it's a good field of view in the southern hemisphere, and in particular to the galactic center of our galaxy, the Milky Way, where we expect a larger flux from dark matter. And most importantly, this telescope also has a high angular resolution for track-like muon neutrinos. I'm going to actually focus on muon neutrinos in this talk. And this is quite important because we are able to really reconstruct and characterize the angular distribution of these neutrinos with KMT-net ARCA telescope. So to constrain dark matter, we basically simulate what will be the angular distribution of neutrinos under different hypotheses. So the null hypothesis here on the left is what you expect in the scheme up under the hypothesis that we only have atmospheric neutrinos. And this basically is the simulation of muon neutrinos, track-like muon neutrinos, after 10 years of exposure with KMT-net ARCA. So this simulation now is compared with an alternative hypothesis, where here instead we simulate the scheme up under the hypothesis where, in addition to the atmospheric neutrinos, we also have a component of annihilating dark matter. So you can see these two scheme up have different anisotropy and properties. In particular, in the case of heavy annihilating dark matter, we have an enhancement of neutrinos coming from the galactic center, which is shown here as the red star. So, making a Monte Carlo simulation, in particular, comparing these two scheme up, so these two different hypotheses, we are able to provide forecast sensitivity for KMT-net ARCA for annihilating dark matter. In particular, this comparison at statistical level, we use the angular power spectrum method. So basically, we expand this scheme up in terms of spherical harmonics, and then we compare the different coefficients L for these two different hypotheses. So thanks to this Monte Carlo and this statistical approach, we are able to provide the expected sensitivity for different channel as function of the matter mass. So here on the left, we have the forecast sensitivity of KMT-net for different leptophilic channel. So the bands here covers basically 9% confidence. Sorry, these are limits at 90% confidence level, while the bands here covers 95% of all the Monte Carlo simulation that we have done under different hypotheses. So these are for leptophilic channel. These are for specific channel where we have the production of 4 leptons or 4 neutrinos in the final states. And here are the case for electroweak boson final states or Cook-Phillips dark matter. So everything above this line, again, is excluded by will be excluded by KMT-net, because the larger is the cross section, the larger is the neutrino flux expected from dark matter. So if you can see here, this region is excluded at the theoretical level given by the unitarity bound. So the cross section can be larger than this value, so cannot be in this range as function of matter mass. So the question is how basically KMT-net will be improving the current constraints on annihilating dark matter. So in this plot here on the left, you can see the comparison of the KMT-net forecast that we have performed with the angular point analysis, compared as current limit with IceCube and Antares, and also a similar analysis made by IceCube with preliminary data using a similar angular pi spectral technique. So as you can see, IceCube is not very powerful for probing annihilating dark matter because it has not a good resolution, good field of view towards the galactic center in the southern hemisphere, while you see that basically Antares and KMT-net are more or less competitive. However, the band here is related to the uncertainties that we have for annihilating dark matter given the different density profile in our galaxy. Indeed, how the dark matter is distributed in our galaxy is not well measured, and in particular there is a huge uncertainty, so how many particles dark matter particles are present towards the galactic center, so at very small radial distance from the galactic center. So these, so on the right, indeed, you see the evolution of the dark matter densities as function of the galactocentric distance for two different well-motivated models. So the so-called and the famous Navarro-Franke White, which is very enhanced toward the galactic center, while in dot dash here you see the bucket profile. So here you see that a galactic center, there is a huge uncertainties on what is the density of dark matter, covering all the uncertainties. However, given the fact that we instead perform a very conservative analysis using the angular pi spectral technique, in particular, since we are not probing the dark matter at the galactic center, but actually we look for large-scale anisotropy, in particular we probe the halo, you see that this uncertainty here on the density is only corresponding to a 40% uncertainties for future limits with KMT-net. On the other hand, this uncertainty for Antares is really covers one order of magnitude and is tracing the uncertainties on the density. So you can see with the bucket profile, for example, that is shown by this dot dash line and the upper edge of the red, the green region here, with angular pi spectrum, in particular with future observation KMT-net, we are going to improve by 2 orders of magnitude the current constraint on the cross-section as a function of the dark matter mass. So this, thanks to the high sensitivity of KMT-net and the angular pi spectral technique, we will be able to really set very robust constraints on dark matter probes. This is very important, especially when we would like to compare the limit that can be placed with a neutrino telescope with other limits, like for example skin on 1 ton, which is our experiment, and for example with gamma rays with Fermi-Lat. So in this plot here, I'm just sketch the case for a benchmark model, which is very minimal, where the dark matter is coupled to a new Z boson with the leptons, and so the key message is that the robust limit we came to net will be really competitive and complementary to other direct and indirect searches for gamma rays with Fermi. So you can see here the green region of KMT-net will be probing a new parameter space, which is still and Fermi-Lat. So the key message is that neutrino telescopes are very complementary and can provide competitive probe for dark matter in this case. So are there any questions on atmospheric neutrinos? Because if not, I'm going to move to the second topic of...
Marco,
yeah.
Can I ask you something? So
yeah.
You're talking about looking for excesses towards the galactic center. And I was wondering, have you guys thought about also looking for excesses in the atmospheric neutrino data, but not in the galaxy, but in like dwarf galaxies?
Oh, here we just really compare these two schema up. So we are not really focusing on the galactic center as normal analysis did. So for example, IceCube and Antares only focus on very small opening angle toward the galactic center. So they are really able to provide strong constraint, but only for profiles that are very enhanced toward the galactic center. So this is why this standard analysis pipeline are largely affected by the halo uncertainty, so astrophysical uncertainties. So in this case, we actually only probing the halo and large-scale anisotropy into the angular spectrum.
I see. So you're letting more possible neutrino decay signal coming from larger volume. Okay. Okay, but you haven't looked outside the halo.
Actually, no. Here we include the galactic component and the galactic component as well. So we include all the possible components coming from the matter. However, we do not include possible signal from point sources that could be like galaxy cluster or dwarf galaxy and so on. So only the galactic component and the diffuse extragalactic component.
I see. All right, thanks.
Okay, so let's move to astrophysical neutrinos. So here,
sorry. I think Johan has a question.
Oh, okay.
So sorry. Actually, it triggered me a question. The question of Mauricio. But so, why is the uncertainty is so low for your method with the decomposition in spherical harmonics here?
No.
So the uncertainty.
Okay. The key point is.
Go ahead.
The point is that, I mean, if you only look for an excess toward the galactic center, so you just look at a small distance here, you really see that there is a huge uncertainties. But then if you extend analysis to the whole halo, you are not having an enhancement in the signal because it's more or less average out, if you want. But then your prediction is more stable under these uncertainties. So here, really, we are comparing the angular power spectrum for these two schema up, while in normal galaxy, you really focus on a few degrees close to the galactic center, and then you compare an almost isotropic atmospheric neutrinos with respect to a very peaked excess within this very small opening angle. So this is the main reason. So we are more sensitive in its analysis to the whole halo rather than to how many particles we have at galactic center or very nearby.
Okay, thank you very much. I understood.
Okay, so let's move to astrophysical. Here, of course, I focus on IceCube data and the potential tension with among different IceCube data and the gamma ray data as observed by Fermilab and possible dramatic explanation of this anomaly, this tension. So very briefly, first of all, I would like to apologize because, of course, only focusing on the matter interpretation of IceCube, and in particular, I will just discuss the key ingredients at the main point that I need to introduce the matter. Unfortunately, I will not go into much detail on all the very interesting and possible astrophysical explanation of these astrophysical neutrinos. So, as you probably know, IceCube has recently released the 7.5 year energy neutrinos events, has events data sample. So here are the number of events after more than 7 years, function of the neutrino energy. So there are more than 100 neutrino events. There is a strong evidence that these neutrinos are not coming from atmospheric background. So they are coming from, they are extraterrestrial neutrinos. They are more or less diffuse flux, so compatible with the extragalactic sources. However, as you know, the origin is still very unknown. Just briefly mention that there are many to produce these energy neutrinos in astrophysical environment. In particular, we can have the production and acceleration of cosmic ray protons, for example, from a supernova remnant. And these high energetic protons can interact with dust and gas. And so we have the so-called hadronic interaction. Or these protons can escape from the source and they can interact with the background photons like CMB or the extragalactic background line. And so we have the production of pions through photodrone interaction. So the key point here is that these, so in both cases, we have the production of charged pions, where we mostly neutrinos, but also the production of neutral pions, where we have the production of photons. So again, also to study astrophysical production is important to consider a multi-messenger approach. So to consider all the possible messenger in neutrinos, cosmic ray, and photons. So given an expected correlation with the injected cosmic proton spectrum, the most simple model that can be used to parameterize the neutrino flux from these sources. It can be a power law, where the neutrino flux is just a power law with a given spectral index alpha. But of course, I mean, depending on different model, astrophysical model, we have different prediction for the astrophysical neutrino flux. And we have, for example, many proposed sources like gamma ray burst, GRP, active galactic nuclei, stardust galaxy, and so on. But unfortunately, I mean, searches of angular and temporal correlation with known catalog of gamma ray sources, in particular the Fermi-Lat catalog, and also stacking analysis, have been placing strong constraints on astrophysical sources, in particular to, I would say, photosources. So on the left here, you see a dedicated analysis given by IceCube, where the percent of astrophysical neutrino produced by GRB is just placed at 1%, while for AGN, or in particular for Blazar, so AGN that points in solar house, depending on the characteristic and the properties of the injected spectrum, these AGN can only account up to 30% of the IceCube neutrino flux. So this is related to photodynamic sources. On the other hand, we could also have the production of neutrinos in proton-proton sources, so in hadronic interaction. So these, for example, are the is expected in case of reservoir, so where the cosmic rays are trapped inside the galaxy, and for example in star-forming galaxy or starburst galaxy. So on the left here, this is, we have the prediction for one of these environment, particularly for proton-proton collision. And you can see that taking into account like the parameter of this source and particular power law flux, the problem is that we have an excess at 100 TeV neutrinos that cannot be accounted for this source, because as I mentioned before, along with neutrinos, there are also being produced photons through directly or through electromagnetic cascade, and so we have strong constraint coming from Fermi-Lat, and so to not oversaturate the Fermi-Lat measurement, we have only this prediction for neutrinos, and so we have an excess at 100 TeV. So all these high energy neutrinos below 100 TeV are more or less in tension with gamma ray data. Just to mention that this, of course, has some mild dependence on the model for this astrophysical environment. And in particular, in this my recent work, we are trying to perform a population study for this astrophysical, for starburst galaxy, so proton-proton sources, in particular accounting for a distribution of spectral index. So going beyond the assumption that these sources have the same properties, the same astrophysical flux. In this study, you see that with this blending model, starburst galaxy, again, can only account up to more or less 40% of astrophysical neutrinos, of hazy neutrinos at 2 sigma. So clearly, even this source cannot be the dominant source in IceCube, for IceCube hazy neutrinos. So considering a more phenomenological approach, IceCube instead has performed a fit considering just a simple power law for the flux. So here is the result in terms of the spectral index and then normalization. Here there is also the component of the prompt atmospheric neutrinos. And so here is the comparison of the fit in terms of spectral index normalization for different IceCube data sample. So is now very slightly, but as you can see, there is I would say 2 sigma discrepancy between a different data sample, in particular the one with the hazy neutrinos and the one only considering true-going muon neutrinos. And you can see that in general, the hazy fit predict a very soft or large spectral index, which is more or less, I would say, in contrast with what is expected by the standard Fermi acceleration mechanism in supernova remnant from proton-proton sources according to the gamma ray fluxes, or from other individual neutrino sources and gamma ray sources, like, for example, the Blazar fit. So there is a slight, in addition to a tension with gamma ray, I would say there is also a slight tension within different IceCube data sample. And also, I mean, this can be also viewed again as an excess, I would say, at 100 TeV neutrinos. And you can see here where I'm showing the residual with respect to a power law flux with respect to index 2.0. So the residual in terms of number of events as function of energy, there is an excess at 100 TeV. And remarkably, this excess is also slightly shown in the Antares neutrino telescope, which is smaller than IceCube, so it has less statistics. So considering this excess has a pure physical origin, it is not a statistical fluctuation. Many scenarios have been proposed to explain it. In particular, there can be a multi-component neutrino flux, where there can be also a subdominant galactic contribution to explain this high neutrino flux at 100 TeV. Or a very interesting scenario is known as hidden sources, where we assume that the astrophysical environment is very thick, so the density of the interstellar medium is very high, so the gamma ray are produced, but then are also absorbed inside the galaxy, and so are not able to escape the astrophysical sources. And so in this case, you have the production predominantly into neutrinos and not in rays, so evading the Fermi-Lat constraint. There can be also, it has been proposed, the decay of neutrino active neutrinos, in particular to alleviate the tension between the all-flavor hazy neutrino with respect to the muon neutrino flux. Or in this talk, I'm going to focus on the case of leptophilic decay in dark matter. So just to give you some highlighted result on this.
So, Marco,
yeah.
Can I ask a question? So what is the combined significance between IceCube and Antares of the excess?
Okay, I don't remember, because I mean, this is almost all the result. I mean, depends on also which data sample you consider. It was around 2.5 or maybe 2.7. I mean, we can have a look at this paper, but of course this is pre-trial. So just considering these energy bin, basically. And also, I would say that also depends on what is the astrophysical component through which you compute the residuals. So in this case, I was only considering 2.0. So this is also quite important parameter to compute the residual and then to compute this tension. However, I mean, what I found interesting is that you have the same behavior in Antares, which is an independent telescope, which is also located in the northern hemisphere. So it is also different systematics and different sensitivity to different portions of the sky. So, for example, this tension could be related to an asymmetry of the northern and southern hemisphere neutrinos, maybe some galactic contribution. So it is quite interesting that we basically start to see the same excess in neutrinos in different elements, even in the smaller one.
Yeah. Yeah. Okay. Thank you.
Okay. So yes. So I'm going to consider leptophilic and dark matter to explain its excess. And again, since the astrophysical component is quite important, what I've done is just to consider two components, flux, that there is neutrinos produced by decay in dark matter, but there is also an astrophysical component where it is minimally parameterized in terms of power law, where the normalization and the spectral index follow a Gaussian prior given the through-going muon neutrino sample. And this is basically the result for the Parameter space. So these are the profile likelihoods in the Parameter space of the dark matter, which are the lifetime of the dark matter as function of the dark matter mass. So on the left, this is for the leptophilic channel, where the dark matter decay into tau plus tau minus. And on the right is the case for the hadronic or quarkophilic channel with BB bar. So the star here is the best fit. The red line, the black line can be regarded as a constraint from the IceCube measurement. In particular, everything below the black line is excluded, because I remember you that in case of decay in dark matter, the larger the lifetime, the smaller is the decay and the smaller is the neutrino flux produced by dark matter. But in addition to neutrinos, there are also, again, taking a multimessenger approach, constraint for gamma rays. In particular, everything below this red line is constrained by Fermi-Lat measurement. So you can see that in the case of hadronic channel, where you have the production of hadronic cascade, so the production of many pions and so many photons, this channel, or I would say the explanation of IceCube, or the IceCube excess in terms of the hadronic field dark matter, is excluded because the best fit, as you can see, is excluded by photons, while instead, in case of electrophilic channel, where the production of photons is not so enhanced, this is not constrained or is not forbidden by Fermi-Lat, so it is still a viable scenario to provide I would say, a second component or a dominant component to the Heise IceCube neutrino measurement. Any question?
So maybe one related question. I think Marcus has one. So Marcus, you want to go first?
I was wondering, so can you repeat the argument again, why these constraints still, so you're basically referring to the leptonic channel on the left, where you basically exclude very short-lived dark matter particles, and the best fit is above the red line, or?
Yes, so yes, indeed. So everything below the black line and the red line is excluded by neutrinos and gamma ray measurement respectively. So the fact is that depending on interaction and the decay channel of the matter, you have a different energy injection, I would say, into neutrinos and into photons. So in the case of hadronic channel, you have a large injection into electromagnetic sector. So there could be electron, positrons, and photons in particular. So this channel strongly produce photons, and this is why these hadronic philic channel are really in tension with the gamma ray data. It's very similar to the case of I would say a hadronic interaction in astrophysical environment. So as soon as you involve the quark, like proton-proton collision or decay to BB bar, to explain the 100 TeV excess in IceCube, you need to oversaturate Fermi-Lat data. On the other hand, if you consider leptonic scenario, you suppress the energy injected into the electromagnetic sector, and this is why you're able to you're not I mean you're not constrained by Fermi-Lat data.
Okay. Thank you.
So maybe related to that, so on the left you're considering a pure branching ratio into tau tau, right? And on the right is pure branching ratio into B bar.
Yeah.
So I wondered, you can let your branching ratios float in your fit, and then you could find something in between. And I wonder if there's a way in which you can claim constraints when also letting the branching ratios float.
Okay, actually, okay, yes. So here, just taking the very minimal and phenomenological approach, as you said, Mauricio. So typically, of course, this branching ratio will depend on the particle model that you have. So this is a prediction of your particle model depending on the parameters. Actually, at the very beginning, I mean, where the first observation of energy neutrinos were performed by IceCube, there was also a paper by Arman, Ismaili, and Seppico, where they tried to explain all the IceCube measurement, including like a mixture of decay channel, in particular with BB bar and with the neutrino line to account for PV neutrinos. So in principle, you can allow the branching ratio to float. And actually, there is also another group that play this game, in particular by Sergio Ruiz and others. But of course, I mean, including an additional parameter, also including like more freedom, so more degeneracy with respect to the astrophysical components or other component that can be in the IceCube neutrinos. But yes, I mean, it could be interesting.
Right. Thank you. I don't see any more hands, so I think we can go on. Yeah.
Okay. Yes, because the point here is that, of course, I mean, you can try to explain the excess or the whole energy neutrinos with dark matter, but the key question here is how we can really distinguish a dark matter signature, a signature of decaying dark matter into neutrinos or in gamma rays with respect to astrophysical sources. And the answer here is again through an angular analysis, since for astrophysical sources, in particular for extragalactic sources, we expect a diffuse flux, while again for decaying dark matter we expect some correlation with the galactic center, so some enhancement with the galactic center. And so in this case, we again, as before for atmospheric neutrinos, we consider an analysis using angular power spectrum just to compare an astrophysical pure hypothesis and an hypothesis where we have a two-component flux, an astrophysical component plus a dark matter. So these are the constraints for IceCube and the forecast sensitivity for KM2net and IceCube Gen 2 using this angular analysis, again, in the parameter space of dark matter, lifetime as function of dark matter mass. So again, here the bands covers the 95% of Monte Carlo simulation used to generate the angular power spectrum sky maps. And so you can see that with KM2net and also with IceCube Gen 2, we will be able to robustly and firmly probe the dark matter hypothesis and explanation of 100 TeV excess in IceCube only through an angular power spectrum analysis, so only considering angular information. So this will be really a robust probe of the dark matter hypothesis, and so future measurements with KM2net and IceCube Gen 2 will really able to shed light on possible dark matter signal in ASN neutrinos, in energy neutrinos. Okay, so in the last part of the talk, I'm going to focus on cosmogenic neutrinos, and in particular on how future measurements of neutrino radio telescope will be able to probe heavy dark matter signature, and also for this case, I'm going to discuss a forecast analysis for decaying dark matter. So going above with the energy, so considering energy larger than 10 PV, we don't have yet observation, rather only upper limits on the neutrino flux in this energy range, but there are many models and components that are expected to appear above 10 PV. In particular, a guaranteed component, I would say, is the so-called cosmogenic neutrinos, here in red. So these, again, are neutrinos produced by the interaction of a very energetic ultra-energy cosmic ray with CMB. So you have the production, again, of neutrinos in this interaction. But also there are other astrophysical environments, like, for example, the case in which in the galaxy there are fast-spinning newborn pulsar. And so you have also these kind of sources, for example, could produce a high neutrino flux here in blue. So actually, this scenario here, so while the cosmogenic scenario is very theoretical motivated and is a guaranteed scenario, here in the case of the blue line, this is the highest flux that is predicted in this energy range. The problem with these predictions in this plot is that they are affected by large uncertainties. For example, in the case of cosmogenic neutrinos, large uncertainties are related to the composition of cosmic ray in a very ultra energetic energy range, or also, I mean, the fact that we don't know how these ultra energetic cosmic ray are produced yet. Or in the case of astrophysical sources, in particular in the case of newborn pulsars, there is also some uncertainties on their astrophysical parameter, this flux. But in the future, I mean, in the next decade, many radio telescope will be built. You can see in this plot the sensitivity for RNO-G, gram 10K, and gram 210K, and also the future IceCube Gen 2 radio, and they will be potentially able to observe these kind of neutrinos. So in this talk, again, I'm going to using these future radio telescope to look for dark matter signature. And then I will consider basically two possible scenarios. I mean, one very conservative, where I consider that this neutrino telescope will observe the highest flux, the highest astrophysical flux predicted, like, for example, the cosmogenic flux or the neutrino pulsar flux, and then I'm going to look for an excess or a bump coming from dark matter in this flux, or I will consider the possible highest sensitivity to dark matter parameter space, where instead I consider that given these uncertainties in the astrophysical counterpart, no observation of neutrinos will be made by neutrinos. So we consider that the expected number of neutrino events coming from astrophysical sources will be 0 in this forecast analysis. So just consider first the case of 0 astrophysical events. So the very simple things that one can do is just to compute the expected number of neutrino events produced by dark matter in the case of decay, so as function of dark matter mass and dark matter lifetime for different experiments. So this number of events, of course, depends on the observation time that we consider 3 years, the FAT area of the experiment, and to get the 95 confidence level sensitivity, this number of events has to match the threshold value given by the Feldman-Cosin approach. So you see in this on the top, this result for different decay channel, again, a neutrinophilic, the dark matter decay into neutrinos, the case of leptophilic, tau tau, and also as I mentioned before, the case of hadronic philic, so the case of BB bar. And the different line, the colored line here, represent different neutrino telescope. So IceCube Gen 2 and Grand 200K will be very sensitive to high energy, ultra energy neutrino flux, and so will be also will provide will be able to explore the largest parameter space of dark matter. So also reaching a lifetime of order of 10 to 29 or 10 to 13 seconds. Of course, let me stress again that in this case we made the assumption that with future observation, I mean, in this energy range, there is a negligible background contamination, and this is a good approach because the rates of background events, for example, in Grand 200K, given its design, is expected to be 0.1 events per year, and this background will be, for example, misreconstructed cosmic ray as neutrinos. But again, here I'm going to consider 0 astrophysical events. So for the highest flux given by the newborn pulsar, we expect actually 20 events, neutrino events per year. In the case of the maximum, the highest cosmogenic neutron flux, we expect 4 events per year. But again, these are affected by very large uncertainty. So it's also reasonable that we will not observe astrophysical neutrinos with this upcoming telescope. Again, it's very important to consider the multimessenger approach because for depending on the channel for heavy dark matter, we also have the production of cosmic ray and the gamma rays. In particular, here the black line represents existing constraint. In particular, here are existing constraints with IceCube, PRG, and Anita using neutrinos. While for BB bar channel, we have galactic, the B line, and extragalactic, the C line, multimessenger constraint by give this author here. So you see again that the BB channel is already quite excluded and constrained by multimessenger analysis, mainly driven by gamma ray observation, while leptophilic channel, for example, neutrinos or tau lepton, are still mostly unexplored. And so neutrino telescope will be very powerful in probing this new parameter space for heavy dark matter. Of course, I mean, to be more conservative, we need to also include the possibility that we actually are going to observe astrophysical neutrinos, again, in the case of pulsar and cosmogenic neutrinos, and assuming that the number of observed events follow is just, let's say, a random variable given a Poisson distribution where the mean value is just the mean number of events expected for different astrophysical sources, we're able to simulate what will be the 2 sigma, I mean the 95 confidence level constraint given different possible observation on neutrino telescope, sorry, of the neutrino events given different astrophysical scenarios. So basically, the region bounded by the lightest the lightest blue color and the darkest blue color represent the possible sensitivity of this telescope on the matter parameter space, that depending on different astrophysical observation. Of course, in the case of newborn pulsars, so the light blue here, where we expect the highest neutrino flux, the corresponding constraints on the matter lifetime are the weakest, because we need a smaller lifetime to account for a large neutrino flux. So this brings me to my conclusion. So today I give more or less a wide overview on possible dark matter probe, in particular heavy dark matter probe in neutrino telescope, ranging from atmospheric neutrinos below 100 TeV up to very ultra energy neutrinos above 10 PeV. And the key message is that in all these cases, neutrino telescopes are very complementary with respect to other probes of the matter, like direct probe in laboratory, or indirect, all the indirect searches like the one with gamma rays. And also, let me stress that the multimessenger approach is very essential to probe dark matter and to possibly find the smoking gun for the matter signature. In the case of IceCube observation, there is a slight tension between a different neutrino data set, and also a tension with gamma rays for neutrinos below 100 TeV. And in this case, the leptophilic decay in dark matter scenario is still viable and can provide a second component to the IceCube neutrino flux observation. And for future radio neutrino telescope that potentially will be able to measure cosmogenic neutrinos, even in this case, neutrino telescope will be very competitive with respect to other multimessenger analysis. And of course, I mean, we need all to stay tuned, because many neutrino telescopes are under construction, will be built in the future, so many new data will come available. So thanks a lot for listening.
Thank you, Marco. It was super interesting. We had a few questions during the talk, but there's time for maybe 2 or 3 questions now.
Yeah, thanks.
So just either raise your hand or write it. I think Marcus has one.
Yeah, hi Marco, nice talk. So you mentioned this power spectrum analysis a couple of times to look for decaying dark matter from the galactic center. I was wondering, I mean, you know where the galactic center is, and you also have, I mean, when you look for decaying dark matter, you have a pretty good idea how the halo looks like. Would it not be more sensitive to do like a spatial template analysis to look for the emission rather than a power spectrum? Because in the power spectrum, you always lose phase information of where the excess is actually in the sky.
No, this is a very good point. Actually, we are discussing about this. I mean, the vision that's point us toward an angular power spectrum technique, in particular, was just to try to build an analysis pipeline, including only angular information, and also to reduce at the same time the uncertainties related to the for example, the astrophysical parameter like the density, the dark matter density in our galaxy. So to be honest, I mean, the fact that our analyses are actually more robust is more related to the fact that indeed we are considering the halo rather than related to the angular power spectrum technique. So we are discussing a lot, very useful to maybe provide and perform a template fitting as you suggest.
Mm-hmm. Okay, thanks.
I mean, yeah, I agree with you.
I had one more question on the last slide. You mentioned TAMBO. I have to confess, I don't know what TAMBO is. Can you say what this acronym stands for?
No, maybe Maurizio. I mean, it would be like a South American.
I'm involved with that, so I should know what it means, but I don't remember what we chose for the acronym. but I can tell you what it is. It's a planned detector for new tau between 1 and 10 TeV, and it uses Auger-like tanks or Cherenkov detectors on the surface. And the configuration is you have a valley, possibly the Colca Valley in Peru. So you put the tanks on one side, you get the new taus interacting on the other side, and then you get the shower of particles hitting the opposite side of the cliff. So you put your detectors there and you see the signal.
Okay.
And we're working on that with Andres Romero Wolf and Stephanie Wiesel and Carlos Argüelles, and see if something can come out. There's some potential funding that we could use from Peru.
So
this would be most related to tau.
That's correct.
At around 10 pp.
Yes,
right?
yes. And the background is pretty low from at least from Andres's simulations. Yeah. So I have actually one question that is not related to Tumbo, and that was related to your couple final slides on the dark matter limits. Yeah, on the lifetime. So I was wondering, you're showing here the limits on the lifetime. I was wondering what you would need to actually see a signal. So let's say if you want to claim a detection at 3 sigma or something like that, what the lifetime should be.
Okay, so here we just consider, so here we basically consider the standard test statistics. I mean, if this is a question where we compare the null hypothesis where we have only astrophysical neutrinos with the one with also including the dark matter. So, I mean, however, this is only constraint. So I don't think that this can be used as to claim a detection. So here we are very conservative still, in the sense that we are not actually consider for example, the energy distribution of these neutrinos, but we only consider the total number of events, and we just look for an excess of the spectra number of events in a given astrophysical sources.
Right.
So
right. I see. Yeah.
This is just, of course, to give an idea of what will be the parameter space of the matter that this future neutrino telescope will be sensitive to.
Mm-hmm.
So I don't know if I answered the question. Maybe.
Yeah, it's fine. I mean, if there is something there when the time comes and we see a detection, then we'll use whatever data is available to actually try to claim it. Yeah, I agree.
Of course, I mean, the problem is that, I mean, depends really on the astrophysical scenarios and on the telescope. Because even with the Grand 200K, we expect, for example, for the more optimistic cosmogenic flux, only 4 neutrino events per year in case of a Grand 200K. So this is why, I mean, it's very unclear if we will have an observation given these uncertainties here, and then if we can really construct the energy distribution of these neutrinos in, I mean, 3 years. This is, I mean, this will be answered with further studies and so on.
For sure. All right, thanks. I don't see any raised hands at the moment. So let me thank you again, Marco. This was really interesting. Thank you for giving us this talk. Everybody, thank you for being here. Marco, I hope we can chat also offline. This was very thought-provoking, so I'd like to continue this. Okay,
yes, I'm very happy to do it. Yeah.
Perfect. All right. Thanks again, and I'll see you, everybody, in a couple of weeks. Okay. Bye-bye.
Thank you very much.
Thank you,
Marco.
Thank you.
Bye.
Bye-bye.
Thank you. Bye.